Hi everybody, I hope you guys are doing well. Unfortunately, we have to be asynchronous also this week, but I'm gonna try my best to cover all the material from chapter 3 that you guys need to know for the quiz, and I hope it will be helpful for you. And next week, we're finally gonna be meeting live. Okay, so let's start. Let's get into it. Let me share the screen. Okay. All right, so in chapter 13, we're talking about solutions. Okay, so we're talking about solute and solvent. The solute is the compound that you have the least amount of, and the solvent is the one that you have the most amount of. Okay, so there's a couple of things to say about solutions. So let's start by talking about what happens when something dissolves in something else. So we talk about delta H of a solution. Delta H of a solution is a measure of the heat that's either released or absorbed when something is dissolved into something else. So the delta H, this amount of heat that's either released or absorbed, depends on three things: delta H of the solute, delta H of the solvent, and delta H mix. Okay, so what are these three things? So these are the three things that take place when something dissolves into something else. So the first thing that takes place when a solute dissolves into a solvent is that the bonds of the intermolecular bonds within the solute molecules break. Okay, and that's delta H of solute. And since we're breaking bonds, that's always an endothermic process. So it has a plus sign. The other thing that has to take place is that the intermolecular forces in between the solvent molecules have to break. And so we have here delta H of the solvent. And because here again, we're breaking bonds, that's going to be positive as well. Now, once both bonds are broken in between solutes and solvent, then solutes and solvents are free to form new bonds with each other. And here you have there you have delta H mixture, and that's always negative. Okay, so you have two terms that are positive and one term that is negative. Depending on the magnitude of these terms, your delta H of solution will be either positive or negative. Okay, so depending if delta H mix is bigger or delta H solvent is bigger, and so on and so forth. Okay. Very often you see these last two terms, delta H of the solvent and delta H mix, grouped as one. It's called delta H of solvation. Okay. Okay, so now what else can we say about this? Let's talk about the effect of temperature and pressure on solubility. Okay, so solubility here is a concept that's closely related to delta H of solution, and that's how much of a solute can dissolve into a certain amount of the solvent. And solubility is affected by temperature and pressure. And it's affected differently whether we're talking about gas, solid, or liquid. So now let's talk about how temperature affects solubility. So when we talk about a solid, solubility of a solid into a liquid, let's say the solubility of a salt in water, a salt like NaCl, for example, or even a non-salt, like a molecule of sugar. So that's considered, a solid, and how that dissolves in water, how much of it will dissolve in a certain volume of water. Well, usually there's a direct relationship between temperature and solubility of solids. Okay, so the higher the temperature, usually the more soluble the solid is. And that is why if you're mixing, some sugar into water, if the water is hotter, the sugar will mix in better and faster, right? It will be more soluble in water. So there's a direct relationship between temperature and the solubility of solids. But when we're talking about gases, there's actually an inverse relationship. And the higher the temperature, usually the less soluble the gases are. And that's because when we talk about solubility of a gas in liquid, we're talking, for example, about when you have like soda and you have your molecules in your gas into a cup of water or a cup of a liquid here. Okay, so you have a liquid and you have some gas molecules inside that have to dissolve into the liquid. So the higher the temperature is, the more these gas molecules are moving faster, the faster they're moving, and therefore the more of them are going to be able to escape the liquid. So actually, the higher the temperature is, the least soluble your gas will be. Okay, so temperature has a direct effect on pressure. Temperature has a direct relationship with solubility for solids, but it has an inverse relationship with solubility for gases. Now, what about pressure? Now, pressure turns out that it does not have much of an effect on liquids or solids. And that's because liquids and solids are already pretty much incompressible. They're already like compact. So even if you increase the pressure on them, the solubility is not really going to change. But when you're talking about gas, solubility of a gas, then pressure affects it and it has direct relationship, meaning the stronger the pressure is, the more the gas is going to be soluble in that liquid. So okay, so for example, like you have some gas particles in the air and you have some water or some liquid here. If you increase pressure on these particles, let's say you have a piston and you're putting it down, as you increase the pressure on them, more particles are going to go inside the liquid and they're going to dissolve. So more pressure means more solubility only for gases, but it has no effect, pretty much no effect on solids and liquids. Okay. So let me clear that. I'm just gonna give me a moment to make sure that everything is going properly with the Zoom. Okay. All right. So let's go. So this is pretty much what I wanted to cover about the theory of this chapter of solubility. Now let's talk about some more numerical, more quantitative stuff about solubility. So the first big topic that we encounter here is the topic of concentration terms. So there are different ways to express how concentrated a solution is. Okay. So I have some questions here prepared, but let me just write them here, write the different terms here with their definition, because it's very important to know the definition. When you have problems and concentration terms, the first thing to do is always to write the definition of the term that we're dealing with. Okay, so molarity. So we have different terms. Maybe the most common one is molarity. Which is symbolized by capital M. And that is moles of solute over liters of solution. Okay, and then you also have molality with an L instead of R. Molality, and that's symbolized by a small m, and that is equal to moles of solute over kilograms of solvent. Okay, so notice the difference here. Here, the denominator, you have solvent only, and with molarity, you have solution at the denominator. Okay, and also don't forget the units. For it to be molality, it has to be kilograms, not grams. Okay, so we did molarity, we did molality. Let me see what else. We have a couple more, like mole fraction. Or mass percent. Okay, so let's just talk about mole fraction. Another term of concentration is called mole fraction. It's symbolized by a Greek X. Like that. Okay, and that's defined as the moles of solute over total moles. So total moles at the denominator is moles of solute plus moles of solvent. Okay. And then you have something else that's mass percent. Then that's very similar to mole fraction, just instead of moles, you have grams, because it's mass percent, and then you multiply this by 100. So it will be grams of solute, or mass of solute, divided by the total mass of your solution. Okay, and then you multiply by 100 because it's mass percent. Okay, so it's kind of like a mole fraction, but it's multiplied by 100. There's also volume percent, in which you will have these two terms in terms of volume instead of mass. Okay. Okay, so there's also other expressions. There are parts per million or parts per billion. So that also depends if it's by mass or by volume. So for example, parts per million, let's say it's by mass, okay? It will be mass of solid over total mass times 10 to the 6th power. Let me erase here. Write it again. Because it might get confusing. So parts per million by mass should usually be specified. Is equal to mass of solid over total mass times a million, which is 10 to the 6th power. And parts per billion by mass would be the exact same thing times 10 to the 9th power. To the power of 9. Okay? So these are the main definitions. So now let's see question 1. Let me just give me a moment, guys. Get some water. All right, so, okay. So that's the question 1. Okay, it's a simple question. And it says calculate the molarity of a solution prepared by dissolving 238 grams of K2HPO4 in enough water to produce 275 milliliters of solution. Okay, so here, simple question, it says we're asked to calculate the molarity. So as we see, every time we have problems like this, questions like this, we want to start by writing out the definition of the concentration term that we want to find out. So because it's molarity, I'm going to write out molarity equals to moles of solid over liters of solution, right? So ignore this one over here. And then the next thing would be to work on finding the numerator and the denominator separately. So first we work on finding numerator, the moles of solid, and then we work on finding the denominators, liters of solution. So how many moles of K2HPO4 we have? Well, we can figure out the molar mass of it. It's 174.74 grams. And at that point here, I combined everything together, but I'm gonna write here the steps, like, you know, the individual steps. Once I know the molar mass of this K2HPO4, I can find out the moles of solute, the moles of K2HPO4. And obviously I do that by doing 200 the grams divided by the molar mass. So the grams was 238 grams. You divided by the molar mass, or you multiply by 1 over the molar mass. 174.78 grams per mole. Okay, and that, I don't know exactly what this number is, but here, actually here. grams. So grams cancel out, and this gives us the moles. Okay. And this is this part. It's the moles. Now, how about the denominator? We have to find out the liters of solution. Well, we're just told that this is 275 milliliters. And so we just have to convert it into liters, because it has to be into liters for giving the correct definition of molarity. And so we're going to take milliliters and multiply it by 1 liter over 1,000 milliliters, 275. So you have the denominator here, which is the liters of solution. Now, I didn't calculate the exact numbers for the numerator and denominator, but once you divide them with each other, you get 4.95 molar. And that would be the molarity of the solution prepared by dissolving that much K2HPO4 in enough water to produce 275 milliliters of solution. Okay. Now, the second part of this question I'm going to skip. There's more, more pressing things that I want to cover. Okay, so question 2. Question 2 is another concentration term question. It says sodium hydroxide is a common ingredient in drain cleaners such as Drano. The mole fraction of sodium hydroxide in a saturated aqueous solution is 0.310. What is the molality of the solution? Okay, so now we're going from one concentration term to the other, right? From mole fraction to molality. So let's write first what we want to find out, which is the molality here, small m, which is moles of solute over kilograms of solvent. And what is it that we know? We know the mole fraction of this, moles of sodium over total moles, and we know that that is equal to 0.310. Okay, so now we want to find out the moles of solute and kilograms of solvent that we have. Okay. Okay, so let's start by finding out the moles of solute. So how do we find that out? Okay, how do we find out the moles of solute that we have here? So in this case, we're given the mole fraction, okay? And since we're not really specified what volume we're working with, the question doesn't say anything about volume. It doesn't mention volume. Usually that means that we can kind of assume an arbitrary volume that we decide that we want to work with, because really the concentration terms do not depend on volume. So we can decide an arbitrary number for volume that we're going to, work with. And the same thing is for total moles. Okay, a very similar concept is for total moles. So, okay, so we were here, and we are trying to find out the molality. So we need to know the moles of your solute. So we know that the mole fraction is 0.310. So let's make an arbitrary number for total moles. And I said, okay, let's assume we have 1 mole in total. So let's assume that we are working with 1 mole of this solution. Okay. And in that case, moles of solute divided by 1 equal to 0.310. It means that moles of solute is also equal to 0.310, right? Okay, so that will be how many moles in that solution. In that solution with 1 mole in total, you have 0.310 moles of NaOH. Okay, so that takes care of this part, the top part of our molality. Now we need to find the kilograms of solvent that we have, right? So how much solvent do we have there? And the solvent is water, because it's a saturated aqueous solution. Okay, so how do we find out the kilograms of solvent, the kilograms of water? Well, we know the moles of water because we made that assumption, right? We said we assume the total moles. We said decided we're working with 1 mole of total moles, and then we found out that in that case we have 0.310 moles of NaOH, and therefore we can say that the moles of water is 1 minus 0.310, and so we have 0.690 moles of water. Okay, but that doesn't help because for molality you need the kilograms of water. But of course, once we know the moles, using the molar mass of water, we can go to grams and to kilograms. And so we take those moles, we know the molar mass of water is 18.02. You have to put that on top so that moles and moles cancel out. So once they cancel out, you can carry on this multiplication, and you get 12.4 grams because the molar mass is in grams. Now, this is still not the final answer because the molality requires the mass of the solvent to be in kilograms. So what we're going to do is just very simply, we're going to convert grams into kilograms, and 12.4 grams is equal to 0.0124 kilograms. Okay, so now we put everything together. The molality of NaOH would be 0.310, okay, which is the moles of NaOH that we calculated, divided by the kilograms of solution, 0.0124, and the answer to that is 25. 25 small m. It means that the molality is 25. Okay. Now, let's do other questions. Here, this one I want to do. Actually, I'm going to cover this one last because this one's a little bit more complicated. I want to leave this for last. Actually, no, I'm trying to change my mind. I'm going to cover that now. Okay. So, okay, so just before we start, this is a question that's relatively complicated. It's a little bit more complicated than what you would probably find in the quiz. And so I just do it for practice because I think if you understand this one, then you're more able to understand many more questions that you're given. You probably won't find such a complex question in your quiz. Okay, so just a disclaimer about that. And this question says, the concentration of iodine in seawater is 60 parts per billion by mass. If one assumes that the iodine exists in the form of iodide anions, what is the molarity of iodide in seawater? And it gives us the density of seawater, which is 1.025 grams per milliliters. Okay, so again, let's start by writing what we need to find, what we're looking for. Let's start by writing that down. So we need to find the molarity of iodide in seawater, okay? Molarity is equal to big M, which is equal to moles of solute over liters of solution. In this case, our solute is iodide. Here we ask for the molarity of iodide. So it's going to be I minus. It's not going to be I2 because that's iodine. Okay, I hope you can all see. Okay, so I hope that you guys can all see. I don't know why this whiteboard is giving me issues. Let me stop sharing the screen and start again. It happens sometimes, I don't know why. Okay, hopefully now it works. So we're talking about the molarity, right? So this is what we need to find, which is moles of iodide. It's because it has here what's the molarity of iodide. So I minus, not I2, divided by liters of seawater. Total liters of that solution. Okay. And now that we wrote what we need to find, let's write down what we know already from the problem. So we know that the concentration of iodine is 60 parts per billion, ppb. Now let's write again the definition of ppb. That's equal to mass of the solute. Well, if it's by mass, in this case, it says that it's by mass. So it's equal to the mass of the solute over the total mass times 10 to the 9th power. And that we said that it's given to, and that we're told that it's 60. Okay. Okay, so now we have to use this information to find moles of iodide and liters of the seawater in order to find the answer to this question. Okay, so we need to find these two things here. Okay, and here we're gonna change things around a bit. Here, I want you guys to see this. So, okay, so we are left that we need to find the moles of I minus. Let's start by that. So the moles of I minus. So how do we find the moles of I minus? Well, we know the, okay, so we know the parts per billion, okay? And if we assume an arbitrary mass that we have, we can solve for the mass of solute, okay? So we can do that in this case. Many times we can do that if we're not told a specific mass or a specific volume that you're working with. We can kind of assume any mass or any volume. So let's, for example, decide that we're working with 100 grams of mass. Okay. So let's say our total mass is 100 grams. Now we can solve for mass of solute. So then grams of iodine, which is I2, right, will be, we have the grams of iodine divided by 100 grams, which is the total mass that we arbitrarily decided, times 10 to the 9 power equals 60. Okay, so now if we solve for grams of iodine, we get that that's equal to 60 times 100 grams divided by 10 to the 9th. Okay, I don't think I have this calculation. We need to do 60 times 100 times 10 to the 9, divided by 10 to the 9th. Okay. And that should give us grams. And let's check let's check using the units that this is correct. 60 doesn't have units, 100 grams is grams, and 10 to the 9 also doesn't have units. So the answer is in grams. So let's see, let's do it without the calculator. So we have 60 times 100 would be 6,000. 6,000 divided by 10 to the 9 is equal to 6,000 times 10 to the negative 9. And that is equal to 6.0 times 10 to the negative 6. Okay, so that tells us how many grams of iodine we have. But that's still not the total answer, because what we need to find here is to find the moles of iodide, not the grams of iodine. But what can we do? We can use the grams of iodine to find the moles of iodine, right? Using the molar mass of iodine. So let's do that. So we have this many grams of iodine here, 6.0 times 10 to the negative 6 grams, multiplied by the molar mass. So 1 mole over, what's the molar mass for I2, for iodide? So if you look at the periodic table for iodine, it's 126.9. If you multiply that by 2, okay. So the molar mass of here, the molar mass of I2 would be 253.8. sorry, this is 253.8 grams of iodine. Okay. Let me try to write that again a little better. 253.8. Okay, and grams cancel out, and we end up with mole of iodine. And now I really need a calculator to do this, unless I have it somewhere. Let me check. I think I did the calculation already. It's easier if I just Google it. Okay, so we wanted to do 6 divided by 252.8. Okay, so that is equal to 0.0236 times 10 to the negative 6. Which is 2.36 times 10 to the negative 8. So 2.36 times 10 to the negative 8 moles. Okay, and that's moles of I2. Okay, so now we're getting closer. Okay, we're getting closer. We need our goal is to find the molarity of iodide, right? So the moles of iodide. So now we have moles of iodine, I2. So if we have this many moles of iodine, how many moles of iodide will we have? Well, it will be double, because each one iodine turns into 2 iodides, right? So you have to multiply this number by 2 to find the moles of iodine. And if you multiply the numbers by 2, it's 4.73. Times to the negative 8. Moles of iron minus. Okay. Okay, so we have this the top part, the numerator part of our molarity. And now molarity at the denominator has the liters of solution. Okay. So when we were trying to figure out the moles, we made an assumption. We assumed that we were working with 100 grams of solution. And so we have to be consistent. When we make these assumptions, we have to make sure we're keeping them throughout the whole time and we're consistent with them. So we have 100 grams of solution, so we have to convert these grams into liters. So how do we do that? Well, using density. So we have 100 grams. Here I put an arrow. So we start with 100 grams times density is in milliliter, 1.025 grams. So let's do that calculation. Let's see if I have it here. 100 divided by 1.025. So 97.56. That's milliliter. 97.56. Okay, 0.561. Okay, that's in milliliters. And then we have to, when I'm converted into into liters, to put it into the molarity expression. What we will need to do is that we will need to multiply, to divide that number. And if you want to go from milliliters to liters, we have to divide that number by 10 to the third. So that is equal to 0.09. Seven, 5, 6 liters. Okay, and now we plug in these two numbers. We're almost done. So let me try to put it in another color. We're almost done to find molarity. Then we continued here in red. We said we had moles of solute, moles of I minus, right? And that was 4.73 times 10 to the negative 8. Okay, divided by the liters of solution, which is 0.09756. And that is equal to 4.73 divided by 0.09756. So 4.73 divided by 0.09756. 9756. Okay, and that gives 49.5. And that would be the molarity. of this thing. Okay. Okay, so I hope this is clear. Again, this is more complicated than what you're gonna find, but it's not so crazy, and it's good to have a good understanding of these concentration terms. Okay, so let's move down. Okay, so now we're going to talk about colligative properties. So colligative properties are those properties that are affected by the presence of a solute into a certain solvent. So, for example, some of the colligative properties, one of the colligative properties involves vapor pressure. And it says that when you put a solute, when you dissolve something into a solvent, the vapor pressure of the pure solvent, the vapor pressure of that solvent decreases. This means that if a solvent, a pure solvent, has a certain vapor pressure, once you add a certain amount of solute, the vapor pressure of the solvent is going to decrease. Okay? And by how much it's going to decrease, it depends on how many particles of solute you have in there. Okay, not on how many grams, not on the mass of the solute, but rather on the particles, how many particles, so on how many moles that solute has in there. Okay. And so that's vapor pressure will be the first of the colligative properties, the first properties that's affected. And that other properties that are affected by the presence of a solute would be the freezing point and the boiling point. And what happens when you add a solute is that the boiling point increases and the freezing point decreases. So it's as if the two extremes are moving further away from each other. When you add a solute to a solvent, the boiling point of the new solution that you have is higher than that of the solvent alone, and the freezing point is lower than that of the solvent alone. Okay. All right, so let's actually do a question on this vapor pressure and how it's affected by the adding of a solute. So the question asks, it says calculate the vapor pressure of a solution prepared by dissolving 0.5 moles of a non-volatile solute in 275 grams of hexane, and it gives us the molar mass at 49.6 degrees Celsius. And it also gives P with the circle. So this P with the circle is the pure pressure of hexane, standard pressure, and it's like, you know, the vapor pressure of pure hexane at that temperature. Okay. Paper. Okay, so let's do this. All right. So there's a formula actually for this. Like there's a formula for each colligative property comes with a formula to numerically quantify how that property is changed. Okay. So here's the formula that the pressure of the solution is equal to the mole fraction of the solvent times the pressure of the pure solvent, P with this circle here, like that. Okay, so in this case, we're talking about hexane. Okay, question was talking about hexane here, because you're dissolving this into hexane. So it would be X of hexane times the vapor pressure of pure hexane. Okay, so and this is called Raoult's law. Okay. So what do we know of these two factors? Okay, so do we know the X of hexane? Do we know P of hexane? So knowing the pure pressure of a substance should be easy because it's a constant at a certain temperature. So we know that it's 400 torr at 49.6 degrees Celsius. Okay, so this is 400 torr. Multiplied by the X of hexane. Okay. So how do we find out the X of hexane? How do we find out the molar fraction of hexane? So the definition of molar of hexane molar fraction is moles of hexane over total moles. How do we know how many moles of hexanes we have? So we know the grams of hexane, and then we can use the molar mass to figure out the moles. So that's what we do. We take the grams, we multiply by 1 over the molar mass, that's grams 2, cancel out, and you get 3.19 moles of hexane. Okay, so now we can find out the mole fraction because we can do 3.19, the moles of hexane divided by the total moles. So the total moles is the moles of hexane 3.19 plus the moles of the compound that's dissolved 0.5. So when you do that, that gives you 0.864. And it's a mole fraction, so it's unitless. And now let's just plug that into the expression. P of solution is equal to 0.864 times 400 torr, which is 346 torr, sorry. So that will be our answer here. All right, so let's go. We still have some things to cover. Let me erase this. I hope this was clear. Okay, so for this one, I don't like this question. I'm gonna skip it. I'm gonna give you guys another example of freezing point depression, the changing freezing point and boiling point. Okay, so let me get a new page. It's here, and let's do a couple more. Okay, so one that I wanted to do is talks about osmotic pressure. Okay, so osmotic pressure is symbolized by this P Greek. I mean the Greek P. Okay, so it's basically what it means physically is that let's say you have the solution, you have your solution with a barrier next to it, and on the other side of the barrier there's just pure liquid, pure solvent. So what happens in this situation, if molecules can pass through that barrier, is that some molecules of the solute will move through the barrier, and they will go to the side where there's less molecules of solute, so that the concentration kind of evens out. Now, the pressure that the movement of these molecules exerts on this membrane is called the osmotic pressure, okay? And it has a formula, okay? Osmotic pressure, P, is defined as mRT, okay, where M would be molarity, okay. R would be the constant here, 0.0821 ATM times liter over mole per K. Okay, and T would be the temperature. So now let's do the question. So this is number 13.104 in the textbook. Okay, and it says a small protein has a molar mass of 1.50 times 10 to the fourth grams per mole. What is the osmotic pressure exerted at 24 degrees Celsius by 25 milliliters of an aqueous solution that contains 37.5 milligrams of the protein? Okay, so you have a solution of 25 milliliters. So you're at 24 degrees, first of all, you're at 24.0 degrees Celsius, and you have a solution of 25 milliliters of a certain solute, okay, 25.0 milliliter, okay, and in this solution you have 37.5 milligrams of protein. And the molar mass of this protein is 1.5 times 10 to the fourth. Okay, so this is again pretty simple, just kind of plug in everything here. So R is a constant, T we know. So let me write down everything that we know here. P is what we need to find. So let's go in order actually. Let me go back and let's go in order. Do we know molarity in order to find P? So molarity, right, is equal to moles of solute, which in this case is the whatever this protein is, moles of the protein, divided by the liters of solution. And the liters of solution is 25, we have 25.0 milliliters, right? And let's convert that into liters. Okay, so this way we have liters. In here we have the moles of the protein. So we don't know the moles of the protein directly, but we know the weight in grams and we know the molar mass. Okay, so we can easily find the moles. So to find the moles of the protein, we need to do the mass, which is 37.5 milligrams, but it's in milligrams, so we want to find it in grams, so that we multiply by 1 gram divided by 10 to the negative 3 milligram. Okay, so that gives us 37.5 times 10 to the third grams. Okay. Okay, so we know that grams, and now we can use the molar mass to find the moles. Okay. So 1 mole. The problem said that the molar mass was 1.50 times 10 to the fourth. Grams. Grams cancel out. And you have the number of moles, which is I don't know exactly because I calculated everything together, but basically here we find the number of moles that we have. And at the denominator, you will have here the liters. So you can divide that by 25.0 milliliters times 10 to the third. Okay, sorry, let me just connect my computer to the battery before it runs out. Give me a moment. Okay, and so, okay, so now we can calculate the molarity. Because we found the moles, we found the liters, and now we can calculate the molarity. Okay, so we have to do it like that. This was the numerator, and this was the denominator. Times 10 to the negative 3. Here. And when we put everything together here, so we're doing 37.5 times 10 to the power of 3 times 1 mole divided by 1.5 times 10 to the 4th. I think here is supposed to be a minus. Yeah, it's supposed to be a minus because this is not a minus here. Okay. Divided by 25 times 10 to the negative 3. So the answer that we get, well, we take this number, this is just the m. So this is will be our m. We take this whole thing and we multiply it by r. Okay. And then we multiply it by our temperature, T, which is, the problem says that it's 24 degrees Celsius. 24 degrees Celsius is equal to 270, here, 297, sorry, 297 degrees Kelvin. So multiplied by R, we multiplied it by 297. And we get the answer, which is 2.44 times 10 to the negative 3. Okay. And that's in ATM. And that would be the osmotic pressure here. Okay. Okay, I think we're gonna end here. And I hope this was helpful, and I hope you guys have an easy time doing the quiz. I hope you guys all do well in your quiz. Okay, let me know if you have any issues. Please email me. Bye.